Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to discuss acid-base chemistry and we're going to cover the following objectives. The first objective is titled definitions. So we're going to start by defining acids and bases according to the Bronsted-Lowry theory. This is a widely accepted model that classifies acids as proton donors and bases as proton acceptors. We're also going to introduce amphoteric species, which are unique because they can act as both an acid and a base depending on the situation. Next, we're going to explore key properties of acids and bases. This includes the autoionization of water. We're also going to distinguish between strong acids and bases that completely dissociate in water and weak acids and bases that only partially dissociate. Then we'll move into polyprotic acids, which are capable of donating more than one proton. This section will explain how each proton dissociates in a stepwise manner and how each step impacts the overall behavior of the acid. Then we'll move into salt solutions. We're going to discuss salt solutions, exploring how salts, which are the products of acid-base reactions, can influence the pH of a solution when dissolved in water. Then our last objective is titled molecular structure and acid-base strength. So here we're going to link molecular structure to acid-base strength. The structure of a molecule, including the electronegativity of atoms and bond polarity, they play a crucial role in determining whether a substance will behave as a strong or weak acid or base. Now, with this introduction, let's go ahead and get started with the first objective. Over the past century, chemists have developed three major definitions to classify compounds as acids or bases. We have the Arrhenius definition, the Bronsted-Lowry definition, and the Lewis definition. For now, in this lecture, we're going to focus on the Bronsted-Lowry definitions, which are built around the idea of proton transfer. A Bronsted-Lowry acid is defined as any species that can donate a proton, or more specifically, a hydrogen ion. This is the hallmark of an acid in this theory. It's something that gives up a hydrogen ion to another molecule. A Bronsted-Lowry base, on the other hand, is any species that can accept a proton. So instead of donating a hydrogen ion, a base is capable of receiving it. So let's take a look at some simple examples. We're going to start here with Bronsted-Lowry acid. Ha is the general symbol for a Bronsted-Lowry acid, and we notice here that it reacts with water. It donates a hydrogen ion to water, and water now forms hydronium ions. This is H3O+. The acid has lost the hydrogen, so now it's just A-. This is its conjugate base. This is the result after the proton is donated. What about for a Bronsted-Lowry base? B is the general symbol for a Bronsted-Lowry base. We notice here it reacts with water. The water is going to give the base a hydrogen ion, and what forms is Hb+. This is the conjugate acid. Now, because the water donated a proton, it is now OH-. It forms a hydroxide ion. Now, from this discussion, we can make note that Bronsted-Lowry acids and bases always occur in pairs because every acid-base reaction involves a proton transfer. One species donates the proton, the acid, and the other accepts it, the base. And this creates conjugate acid-base pairs. So for example, let's scroll down here and take a look at this reaction. This is a reaction of water with itself, autoionization, and we get the following reaction. Now, this water is going to act as an acid. I'm going to highlight it in blue. And this water acts as a base. I'm going to highlight it in red. Now, this water that acts as an acid it's going to give a hydrogen ion or a proton to this other water molecule that serves as the base. When it gives this other water molecule a hydrogen, it now forms hydroxide ions. Now this hydroxide ion, this is the conjugate base of the acid water. So now we formed a conjugate acid-base pair. This is the acid, and this is the conjugate base. What about for the water that acts as a base? So this water receives a hydrogen ion to form H3O+, hydronium ions. So that means that this product is the conjugate acid, and this base and conjugate acid, they form conjugate acid-base pair. So again, Bronsted-Lowry acids and bases always occur in pairs because every acid-base reaction involves a proton transfer. So just to summarize here, one water molecule acts as the acid, donating a proton, while the other acts as a base, accepting the proton. The result is a hydronium ion, the conjugate acid, and a hydroxide ion, the conjugate base. And this helps illustrate the concept that acids and bases always exist as pairs in reactions. Now that we've defined Bronsted-Lowry acids and bases, let's dive into another important concept, amphoteric substances. An amphoteric substance is one that can behave both as an acid and a base depending on the environment it is in. An amphiprotic substance is a type of amphoteric substance, and it is one that can accept or donate a proton. An example of this is water. When an acid is added to water, water accepts a proton and behaves as a base. When a base is added to water, water donates a proton and behaves as an acid. Now, this dual behavior is really crucial in many chemical reactions, particularly those involving acid-base equilibria. Additionally, conjugate species of polyvalent acids and bases, they can behave as amphoteric or amphiprotic substances. This means that certain conjugate acids and bases can switch between acting as acids or bases depending on the surrounding conditions. Now with that, we can go ahead and move into the second objective. Here we're going to cover properties of acids and bases. Acids and bases are usually characterized according to their relative tendencies to either donate or accept hydrogen ions. Furthermore, aqueous acid and base solutions can be characterized according to their concentrations of hydrogen and hydroxide ions. I want to start this objective by saying when we say hydrogen ion concentration or hydronium ion concentration, we're talking about the same thing. This is going to be really important because we might alternate in what form we use, and it's important for you to keep this in mind. Now, the first topic of conversation here is the autoionization of water and hydrogen ion equilibria. While we've mentioned this earlier, I think repetition is key. The autoionization of water, also known as the self-ionization of water, is a process where water molecules react with each other to form hydronium and hydroxide. This reaction is essential in understanding the acidic and basic properties of aqueous solutions. In this reaction, one water molecule donates a proton to another water molecule, forming hydronium ion and hydroxide ion. Now, this reaction is reversible, meaning that hydronium and hydroxide ions can recombine to form water. And it's important that this reaction is reversible because that means we can write an equilibrium constant for this reaction. The equilibrium constant for this reaction is called the water dissociation constant. It's denoted as Kw, and it's given by the following equation you see here. Now, just as a friendly reminder, Equilibrium constant expressions are the concentration of the products raised to their stoichiometric coefficients over the concentration of the reactants raised to their stoichiometric coefficients. And remember, we do not include solids or liquids. So looking at this equilibrium constant expression, we have the concentration of hydronium ions and hydroxide ions, and there's nothing in the denominator, and that's because both reactants are liquids, which we do not include in the equilibrium constant expression. Now, the water dissociation constant, this is equal to 1 times 10 to the minus 14. This value indicates that in pure water, at 25 degrees Celsius specifically, the concentrations of hydronium and hydroxide ions are both 10 to the minus 7 molar. And that makes sense. If they're both 10 to the minus 7 molar, then their multiplication gives rise to 10 to the minus 14. Now, again, as a reminder, the equilibrium constant for the water dissociation, this is 10 to the minus 14 at 25 degrees Celsius. So unless the temperature of the water is changed, the value for Kw cannot be changed. Next, I want to further explore hydrogen ion equilibria. Hydrogen ion equilibria refers to the balance between hydrogen ions and hydroxide ions in aqueous solution. The concentration of these ions determines the pH and pOH of the solution. Now, a p-scale is defined as the negative logarithm of the number of items. Let me elaborate. When we see pH, P indicates negative logarithm, and the H tells us what we're taking the negative logarithm of. So pH is the negative log of the concentration of hydrogen ion concentration. Similarly, pOH is going to be the negative log of the hydroxide ion concentration. pH plus pOH is going to be equal to 14. Now, I want to elaborate on this because we need to understand the scale for pH and pOH and what the numbers indicate in terms of acidic versus basic solutions. When an acid is added to water, it increases the concentration of hydrogen ions. It increases the concentration of hydronium ions. So for instance, if you add hydrochloric acid to water, this is going to result in an increase in hydrogen ions. And this is going to lead to a decrease in pH. So on the pH scale, anything below 7 is considered acidic. On the other hand, when a base is added to water, it increases the concentration of hydroxide ions. So for instance, if you add sodium hydroxide to water, this is going to result in an increase in hydroxide ions, which results in a decrease in the concentration of hydronium, and that leads to a higher pH. So any value of pH greater than 7 is considered to be basic. When pH is equal to 7, then the solution is neutral. Now, similarly, what about pOH? So this is kind of the opposite of the pH scale. If you're dealing with an acidic solution, it's going to have a pOH greater than 7. And for the basic solution, its pOH is going to be less than 7. And again, if it's equal to 7, then the solution is neutral. Now, this is a lot of information, so I want to go ahead and take all of this stuff that we've discussed and kind of summarize it in one page in an organized way. And this also allows us to repeat the important points that we need to keep in mind and also connect everything together. Now, like I said previously, when we're talking about hydrogen ion concentration or hydronium ion concentration, we're talking about the same thing, and you might see me use either form when discussing hydrogen ion concentration. To that point, if the concentration of hydrogen ions is greater than the concentration of hydroxide ions, then the solution is acidic. And that means that the pH is below 7. On the other hand, if the hydrogen ion concentration is less than the hydroxide ion concentration, then the solution is basic, which means that the pH is greater than 7. If the hydrogen ion concentration is equal to the hydroxide ion concentration, then the solution is neutral. The pH is equal to 7. Now, this relationship allows us to easily categorize solutions into acidic, basic, or neutral based on the concentration of these ions. And actually, I'm going to scroll down here really quickly. This is another way to format this information. So what this table tells us is that if a solution is acidic, it's going to have a pH less than 7. And that means that the hydrogen ion concentration is going to be greater than 10 to the minus 7 molar. And the hydroxide ion concentration is going to be less than 10 to the minus 7 molar. If the solution is basic, the pH is going to be greater than 7, and the hydrogen ion concentration is going to be less than 10 to the minus 7 molar, and the hydroxide ion concentration is going to be greater than 10 to the minus 7 molar. If the solution is neutral, pH is equal to 7, and the concentration of both hydrogen and hydroxide ions is equal to 10 to the minus 7 molar. Now I want to scroll back up to this table right here. This summarizes a lot of these equations we've talked about thus far. In this first box, we have our equations for pH and pOH. So pH is equal to the negative log of the hydrogen ion concentration, and pOH is the negative log of the hydroxide ion concentration. Again, at 25 degrees Celsius, the sum of pH and pOH is equal to 14. Now, this is a really important relationship because if you know the pH, you can easily figure out the pOH. It's just going to be 14 minus pH. And also, this means that you are able to convert back and forth easily between these scales. In this second box, this shows us the water dissociation constant, which is the equilibrium constant for the autoionization of water. This is just going to be the hydrogen ion concentration multiplied by the hydroxide ion concentration, and that's equal to 10 to the minus 14 at 25 degrees Celsius. Sorry, that was my TV. We're going to ignore that, move forward. All right, in this third box, this touches on the water dissociation constant again. And here we notice that the pKw is just the negative log of the water dissociation constant, and that's going to equal 14 at 25 degrees Celsius. This also helps us figure out the origin of this relationship right here, where pH plus pOH is equal to pKw, which is equal to 14. And then in the last box here, I like these relationships. This is so helpful. If you have the pH or the pOH, you can figure out the hydrogen or the hydroxide ion concentrations respectively. So to figure out the concentration of hydrogen ions, this is just equal to 10 to the minus pH. To figure out the concentration of hydroxide ions, that's just 10 to the minus pOH. So this helps you interconvert between different things depending on what you're given in a problem and what you need to figure out. So the takeaway from all of this information is summarized in this table right here. So all of your important equations are right there. Now with that, let's put this into effect and tackle a practice problem together. This problem says the hydronium ion concentration of a particular aqueous solution is 3.7 times 10 to the minus 4 molar at 25 degrees Celsius. Determine the pH, the hydroxide ion concentration, and the pOH of this solution. Okay, wonderful. We know the concentration of hydronium ions. We're given that in the problem. So calculating the pH is going to be really easy because pH is just equal to the negative log of the hydrogen ion concentration. So this is going to be the negative log of 3.7 times 10 to the minus 4. And if we plug this into a calculator, we're going to get 3.43. So this is our pH. Now that we know our pH, we can determine our pOH because we know that pH plus pOH is equal to 14 at 25 degrees Celsius. We can isolate the variable pOH. That's going to be equal to 14 minus pH, which is equal to 14 minus 3.43. This gives us 10.57. So we have our pH, we have our pOH. We need to figure out our hydrogen ion concentration. Now to figure out our hydrogen ion concentration, this is just going to equal 10 to the minus pOH, which is equal to 10 to the minus 10.57. And if we plug this into a calculator, we're going to get approximately 2.7 times 10 to the minus 11 molar. And there we have it. We've solved this problem. Now we can move on to our next topic. Here we're going to discuss strong acids and strong bases. Strong acids and bases are substances that completely dissociate into their ions in aqueous solution. This complete ionization makes them highly effective in altering the pH of solutions. Strong acids are characterized by their ability to completely dissociate in water, releasing a high concentration of hydrogen ions. And this complete dissociation is what makes them strong acids. Strong bases are compounds that completely dissociate in water to release hydroxide ions. And again, this complete dissociation makes them strong bases. Now, for this general chemistry course, there's a list of strong acids and strong bases that you should commit to memory. If you encounter any of these, you should be able to identify them as strong acids or bases. Now, for strong acids, we have hydrochloric acid, hydrobromic acid, hydroiodic acid. We have sulfuric acid, nitric acid, perchloric acid, and chloric acid. So those are our 7 strong acids. For strong bases, we have lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. So here we have 8 strong bases. Okay, let's keep that in mind and let's tackle a couple of practice problems. This first one says, what is the pH of a 0.0082 molar nitric acid solution? Okay, so we're dealing with nitric acid. We know that this is a strong acid, which means that it completely dissociates in solution. And because it completely dissociates and ionizes in aqueous solution, then the concentration of hydrogen ions is going to be the same as the initial concentration of the strong acid. And that's really important to keep in mind because we can use that to calculate pH. So just to write this out, we have nitric acid, all right, plus water in solution. And this is going to dissociate in water as NO3- plus H3O plus hydronium ion. And because this is a strong acid, we have 0.0082 molar nitric acid. When it completely dissociates, we form 0.0082 molar hydrogen ions or hydronium ions. So now with that information, we could just plug it into our equation for pH. pH is negative log of our hydrogen ion concentration. So this is just the negative log of 0.0082. If we plug this into a calculator, we're going to get a pH equal to 2.09. And this answer makes sense because we're dealing with a strong acid, and this value indicates that it is indeed an acid. Let's tackle another one together. This problem says, what is the pH of 0.0026 molar potassium hydroxide? Now, potassium hydroxide, this is a strong base. Let's keep that in the back of our head. Whenever you're asked to determine the pH of a solution, you should focus on the chemistry of the solution. Now, for this question, we know that potassium hydroxide is a strong base, and that means it completely ionizes in aqueous solution. That means that potassium hydroxide in water dissociates into potassium cations and hydroxide anions. And again, because it's a strong base, the concentration we start off with is the same as the concentration of hydroxide ions that we form. Now, we want the pH, but we're given enough information to figure out the pOH, and then maybe we can work backwards to get the pH. The pOH is equal to the negative log of the hydroxide ion concentration, which is what we know. So we're going to go ahead and plug this into the equation. Negative log of 0.00026. This is going to give us a pOH that's equal to 3.59. Now that we know the pOH, we can figure out the pH because pH plus pOH is equal to 14. And if we were to isolate this pH variable, that would give us 14 minus pOH. That's equal to 14 minus 3.59. And that is equal to 10.41. So the pH is 10.41. That makes sense because we are dealing with a basic solution. Now with that, we're going to go ahead and stop the video here. In the next lecture, we're going to talk about weak acids and bases and how we handle solutions with weak acids and bases. I hope that this lecture so far has been helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.